lousy weather outside, but it seems that the weekend is going to be shaped up to be a good one before it dips down to cold temperature. All right, so good morning again. The Lord is risen. Alleluia, alleluia. Truly he is risen. Alleluia, alleluia. Still Easter season for another 3 weeks or so. All right, good. Well, let's start the very last part of energy today. Just before I move on, a couple of things I'd like to sort of mention. I don't remember like which student asked the questions, but the student asked me like if the microscopy potential energy depends on density, and I said, well, I was thinking about this. I was not sure here, and now that we've discussed a little bit about change of states, um, yeah, the microscopic potential energy will change a little bit, but just slightly as a function of the density. The microscopic potential energy will change mostly when there's a change of state. When there's a change of state, there's a real new intermolecular forces at play. So this is where the microscopic potential energy really does change. Otherwise, like for the same state, does it change with density? Yes. Okay, the particle are a bit like closer together, and since the microscopic potential energy depends on the intermolecular forces, well, as the particle get closer, I guess their molecular forces are a bit like different, right? But the key point is a bit different, and it's not going to matter too much. Um, Another one, like I think someone asked me, like, where does Q come from uh, in um, in thermal energy? Heat. Why do we use Q? That comes from actually it stands for quantity. Q stands for quantity of thermal energy, or what they used in the past, quantity of thermal energy. So that was the first time used by a French physicist by the name of Clépeyron, who did like a lot of work on thermal energy, thermodynamics. All right. Does anyone have any question before I start? I hope you have your document right with you. So make sure if you don't have it, like make sure you have either a print, or because you'll have to write on it, or a iPad where you can write on it. Okay, so no questions? All right, Matthew Chong. I have no Matthew Chong. No camera, no nothing. Matthew, can you chat with me a second? You tell me here, like, can you communicate with you? Matthew Chong? Chat, chat, chat. Chat quick. No chat? Hey, be very careful because I'm going to kick you out here. Matthew Chong. Are you there, Matthew? Okay, does anyone know if Matthew is alive? I hope he is. No, I'm pretty sure he's alive. But Matthew, okay, so let me chat with him. Yeah, just ask him like, well, test him. So bad English. Anyway. Okay. All right. Oh, there's 43. There's one more people than necessary. So we just came in here. So this is very important, guys, that Key, Matthew, Leo, Catherine. Okay. All right. So let's start.
Hello?
Oh, yeah.
Hey, sorry, I had a problem connecting.
Good. All right. So glad to hear you. Okay. So let's start with this here. So you don't have to write the next part. All right, just listen here. So let me share this a little bit higher here. Mm. All right, good. So don't write this down here. So today we're going to sort of talk a little bit about nuclear energy. Um, Now, when Rutherford discovered that the atom was made of a very, very dense core that was positively charged, um, and then most of it was empty space. Then a little bit later on, well, they find out, of course, that the electrons, whose mass are very, very, very small and consequential compared to the core, the nucleus. So the electrons are going around the nucleus. Then they realized here that the core, the nucleus, is made up of smaller subatomic particle called protons, and all those protons are, of course, positively charged. All right. So why is it that forest is positively charged? Now, this is a bit of a problem that physicists had in the 1920s when they discovered here that the nucleus is made up of protons. All right, and protons are all positively charged. Now, if you think, of course, that nucleus is made up of tiny particle called protons are positively charged, physicists ask themselves, how can the nucleus stay the way it is? All right. Why is that? Why is this? Like once physicists discovered that the nucleus was made up of tiny particle protons that are positively charged, they started to ask the question, how can a nucleus be stable? So why do you think that they came up with this questions? Okay, Max here, only Max. Anyone? Yeah, Catherine.
Well, because they would repel each other.
Exactly. So here you know that from the law of electrical charges that like charges repel and unlike charges attract. So that was a bit of a problem. They knew that the nucleus was very, very small. They knew that those tiny particles, super, super close together, and they knew that the electrical repulsion, the force of electricity, the electrical force of repulsion, is enormous at small distance from another. It's enormous. So the question was, well, how can a nucleus stay the way it is? Why don't all the protons like fly as far apart from each other as possible? So in order to come up with an answer, they had to presume that there was another force acting at the nuclear level, another force that would sort of bind those subatomic particles together, an attractive force that would sort of bind it, that would be even stronger than the electrostatic repulsion. And this force is called the strong nuclear force. So in the nucleus, there's two type of forces at play. The strong nuclear force that allows like those subatomic particles to. How many times is he gonna come in like Forrest? Does Forrest have like problems with? Anyway, so so here like the strong nuclear force that binds those subatomic particles together, and then you have the electrostatic force that wants to push it apart, wants to break it apart. Okay, so of course, if a nucleus is to be stable, the strong nuclear force has to be stronger. The attractive force has to be stronger than the repulsive force. All right. Now you also have neutrons. Well, the neutrons, they're neutral, so they're not going to sort of change much in terms of repulsion. It might sort of ease up the repulsion between protons when you have like neutrons in the way. Neutrons in the way, well, it's a little bit better, right? They're farther apart, so the electrostatic repulsion is less, but still, it's still enormous. So the strong nuclear force here is a force that binds not only the protons together, but also protons and neutrons together. Okay. All right. So now that we have this, let's start like, whoops, let's start taking notes here. So nuclear energy. Yep, there you go. So nuclear energy.
Oh, wait, should we write this on the printout?
Yeah, you write this. I said like you can write it now. Okay, is Forrest back? What's wrong, Forrest? Problem with your connection?
Yeah.
Okay, you're there now? Okay, good. So nuclear energy here. So the stability of a nucleus depends on a delicate balance between the repulsive electrostatic force, okay, between protons and the attractive nuclear force. Nuclear force. It's called a strong force. There's a weak force too. The weak nuclear force also acts, is at play only at the nuclear level. And it's kind of a destabilizing force. Anyway, I'm not going to get into details of this. Okay, so stability of a nucleus depends on delicate balance between the repulsive force and the attractive nuclear force. So when the electrostatic force is greater than the attractive nuclear force, okay, the nucleus breaks apart. All right, so nucleus breaks apart in smaller fragments. Smaller, more stable fragments. All right. So when this happens, so we say therefore that the nucleus is radioactive. There you go. Say it is radioactive. So radioactive material is a material whose nuclei, this is one nucleus, two nuclei, whose nuclei are unstable. So they're going to break apart. And so that's what radioactivity is. Radioactivity is nothing else but nuclei breaking apart, okay? Because the electrostatic force is much greater than the attractive nuclear force. So those protons cannot stay together, they fly apart. Or they break down into smaller fragments, okay? Yeah. Now let's do a little bit of review of chemistry. Well, you've learned this in chemistry, but it's really physics, right? Well, everything is physics. Not everything is physics, but I mean, everything that's matter and energy, yes, is physics. Okay, so nuclear breaks apart and is smaller, more blah, 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 blah. Okay, couple of things here. So a nucleus is made up of nucleons. All right, so it's made up of nucleons. Right, and there are two types of nucleons. So what are two types of nucleons? I'm waiting. Two types of nucleons. What do we have? Yeah, they.
Protons and neutrons.
I cannot hear.
Protons and neutrons.
Yeah, proton and neutron. All right. So these are two types of nucleons. All right. Okay. Review standard atomic notation. All right, so let's put a chemical symbol here. So let's put, I don't know, put what? Boop, boop. So let's put lithium. What's lithium here? I don't have this. Is it 3? What's the atomic number? Is it 3, guys? Lithium? What's the atomic number of lithium? Is it 3?
Yes.
Yes, okay. All right, so let me sort of put this here. So the standard atomic notation. Atomic notation is this. So on here, it's going to be the atomic number. And right here is called the mass number. Okay. And this is the element. So this is the element, the chemical formula for the element. All right. And you might sort of remember the atomic number. What does the atomic number gives? So the atomic number gives. Come on, quick. Not always the same. Timothy.
Number of protons.
Number of protons. Very good. Now, what's the mass number gives you? This mass number gives you. Not atomic mass. I didn't say atomic mass. Jason.
The number of protons and neutrons.
That's correct. So number of nucleons. All right. So this is the number of protons plus number of neutrons. There we go. All right. All right, so example. Just before I do an example here. So elements that have, and what determines the nature of an element is, of course, the number of protons, right? That's what determines, right? So elements that have a different number of neutrons, right? But same number of protons. Are called, or does anyone remember what they're called? Okay, some other people, come on. Come on, give me some other people. Some other people, okay, some other people, come on. Okay, still it's always the same. Okay, Eric, you. Eric?
Isotopes.
Isotopes, right? Right, so remember this? Okay, so example. So lithium, you told me it's 3. I hope it's 3. So 3, here we're going to put the mass number. So let's say here it's 5. So by the way, here we're doing nuclear physics. We do not care about electrons. Electrons are involved in chemical reaction. We're not doing chemical chemistry here. We're doing nuclear physics. The electrons are of no consequence, no whatsoever in here. Okay. So when we refer to this here, this is the nucleus itself, right? Okay. So this one here is called lithium 5. All right, so here the mass number here. So we put the lithium, the name of the element, a dash like the mass number. Okay. Now, of course, you remember here, so number of neutrons. Remember the formula here. If I want to find the number of neutrons in the nucleus of lithium 5, what do we do? Come on, grade 9. So not always same. Come on. And some other people. All right, give me. Adrian. Now, Adrian doesn't have a speaker? Yeah, he has a speaker. Yeah, Adrian. You remember how to find number of neutrons? Adrian Lee. Adrian. Adrian, are you there? Not there, I'm going to kick you out. All right, mic is broken. Really? Okay, well, type to everyone. So number of neutrons is equal to what? Adrian, chat. Are you typing? Is he typing? Yes, very good. So yeah, so it's a mass number minus the atomic number. Excellent. All right. So if I want to find the mass of number of neutrons in this one, it's of course here it's going to be like 5 minus 3, and you have 2 in this particular case, right? Right, number of neutron, this particular case. Now another isotope of lithium might be this one. So it has to be 3, right? This would be called like lithium 4. Okay, and so on and so on. Once again, the atomic number determine what element it is, and 4 is the total number of nucleons, so total number of protons and neutrons. Okay, we're good. All right, so now that we have this, like find this here in your notes. So just find it. All right. Okay. Let me sort of do something else here. So when a nucleus breaks, when a nucleus is radioactive, breaks apart, we say that it decays. It decays. Okay. Say that it decays. Okay. So decaying means that the nucleus will break into smaller fragments. Before I put this here, another example here of a very important example is this here. This is helium 4. This is also given another name. It's called alpha particle. So that's a symbol for alpha particles, or alpha radiation. So helium 4 is alpha. So when Rutherford investigated the nature of the atom, what he did, he had like a little gun, and it was shooting helium 4 nuclei. And he called them like alpha particles at the time. So it was an alpha gun. All right, so let's go back to this here. Everyone is okay with this? Okay, give me a shout if you're not quite ready. Okay. All right, so let's do this here. Okay, so in any decay, well, so you've learned a couple of different conservation laws so far. You've learned conservation of energy. What's another conservation law that you may have learned in the past? Any, Madav?
Conservation of mass.
Well, that's not totally true. That's what a chemist would say, but chemist is wrong. We're gonna find this next year. That's a good try. What else? Yeah, Jeffrey?
Angular momentum.
What, have we learned about angular momentum? No, don't give me things like that you haven't learned. Things that you have learned. It's true though, but we don't know. We don't know. Come on, grade 9. Grade 9. Yeah, Eric, Hugh.
Conservation of matter.
No, you did not learn this in grade 9. What did we do in grade 9? What was the physics part of grade 9? Max?
It was about like
what?
Circuits. It was about circuits.
Yeah, well, about electricity, right? Is there something that you know about electricity? Remember, conservation means that something does not change with time, right? Any idea, guys? No? All right, so Allison? No, okay. It's conservation of charge. Charge is neither destroyed. The total charge is neither destroyed nor created. Okay. There's as much total charge in universe now as there was like right after the Big Bang. Okay, we never come across a case where the total charge have disappeared. So charge is constant. All right. So it's called conservation of charge. Okay, there are other conservation laws, and one of them is called conservation of nucleon number. Oh, by the way, where did I put this here? The nucleon number, so let's go back to this. Nucleon number is the mass number here. So this is also called nucleon number. Okay, so let's put this here. Okay, so the mass number, it's also called the nucleon number. And this is given the symbol A. Okay, I forgot to do that here. And the atomic number, well, the atomic number, Z is the charge. Okay, so Z is the charge. So let me put it here. Atomic number is also Z. Okay, so it's a capital Z. There you go. Okay. Yeah. So this one here can be written as this here. So AZ. I should have put this like before. Ugh. Okay, so let's put it here. Yeah, that's fine. Okay. Apologize for this. So the mass number is also called nucleon number because that's what it is. It's the number of nucleons, and it's given the symbol A. The atomic number is given the symbol Z. That refers to the charge of the nucleus. Okay. All right. So go back here. So in any decay, any transformation here, we have a conservation nucleon number. So the number of nucleon doesn't change, and the number of charge, the total charge does not change too. It doesn't change. These are conservation laws. And all of physics actually is subsum in about like 7 conservation laws. All right. So you're going to learn some more next year: conservation of angular momentum, conservation of momentum, and you're going to learn also other laws as well. Okay, so there are 3 major types of nuclear decay. The first one is called the nuclear decay. Alpha decay. So what happens here is, like, you have your nucleus here with the mass number A and charge Z. And then what happens here is that it splits into 2 parts. It splits into an alpha particle, which is nothing else but helium-4, plus a new nucleus. Notice these are nuclear reactions, right? So these are nuclear reactions here. So you got your reactants here, your reacting nuclei, and you have your products, your resulting nuclei, okay? There's no electron in the picture. We're not doing chemistry now. We're doing like nuclear physics. Okay, so that's a general, and has since helium carries a charge of 2, and the initial has a charge of Z, and charge is conserved. So that means that this new element here, this new nucleus here, will have Z minus 2. Well, since the number of protons determine the nature of the element, what happens here is that X has been changed into Y, all right? And then the nucleon number, since the nucleon number has to stay the same across, so if you start with A, helium-4 has 4, so this new element here must have A minus 4, right? So it's pretty easy here. So let's do this one right here. Find the unknown elements as well the nucleon and Zen number in the alpha decay of cobalt-61. So cobalt-61 is radioactive. It's kind of unstable. It will sort of break. And most often, I don't know, most often than not, but one way that it can break apart is by alpha decay. So alpha decay, you always have like helium plus unknown here. So how are we going to find this unknown element here? Well, let's do this. So the A number is conserved. So how much do you have on that side? Well, you have like 61. How much do you have on the other side? You have 4 plus the unknown here, A, right? So by conservation of nucleon number, so you can figure out like what A is. So A is, oh, this is big. Okay, so A is 61 minus 4. So that will give you 50. I don't know why I have so much problem these days. I'm really getting old. 57. All right. Now, what about Z? So the charge is conserved. So what do you have on the reacting side? You have 27. What do you have on the other side? You have 2 nucleus plus Z, the unknown. So you just isolate for Z, and you find that it's 27 minus 2 equal 25. Now, if you want to know what element is this, you have to look up on the periodic table. So take my periodic table right here. So you look up at your periodic table and tell me which element is this. So you have a periodic table, I think, on your textbook right here. Yeah, David Burma. What do you mean you're gonna guess? What do you mean you guess? You guess? Wow, you're good. All right. Yeah, this is manganese. That's correct. It's manganese. But manganese what? Manganese what, guys? Yes, if you want, yeah. That's correct. That's correct. So this one here is manganese. All right, I'll put your N, your famous N. I don't like this N, but anyway, so this is 5725. So it's manganese 25. That's correct. Okay. I put like manganese. There you go. No. Manganese. There we go. All right, so I'm gonna keep my, so make sure you have a periodic table. Okay, are you good for this? Yes, Max. You still have your hand lowered? No?
No, I have a few questions.
Yeah.
So the first one, so usually in chemistry, so when we write the elements, the teachers, when we write out the name of the element, they won't let us use capital letters. Do you care if we use like capital M in
You mean for what? For this?
Yeah.
Oh, those chemists. No, I don't care. Okay, so.
Okay, wait, no. I also have another question.
Yes.
So you know how you said cobalt 61 is radioactive, right?
Yeah.
So how do you like? So how does it exist? So how does it exist to begin with? If it's like unstable.
Can you wait?
Sure.
Thank you. Okay, so I'll answer this at the end. Okay, another type of decay, it's called beta decay. So right here, beta, and there's two types: a beta negative, beta minus decay. So a beta minus decay, what happens here is that a neutron will become a proton. So a neutron will become a proton. So now remember here that a neutron and protons are both nucleons. So when a neutron becomes a proton, the nucleon number does not change. So you start with A here, you still have A. However, charge must be conserved. So if a neutron, like here in X, if a neutron becomes a proton, there's a positive charge that has been created, right? It must be offset by a negative charge. In this case, you're going to have a electron. So electron here, this is the charge of electron. You see here minus, so that's the symbol E, little e. This is the charge of an electron here, -1. And of course, it's not a nucleon, so it's 0, all right? Next year, I'm going to talk about this here. This was discovered much later. There was another particle also produced. And this particle here, it's called a anti-neutrino. Okay, it's an we'll talk about antimatter next year, okay? All right. Okay, so now if the charge is to be conserved, so if it turns into protons, so this new element here will have one more proton than before, so it'll be Z plus, but it has to be offset by an electron here, -1, right? Okay, so let's do this one here. So find the unknown element as well, nucleon and Z number in the beta minus decay of uranium-239. Now, uranium-239, uranium is a huge, it's the natural element with the most protons in it. Past 239, past the atomic number of uranium, you have to force protons together, okay? It's not made by nature, all right? So uranium-239 packs packs like 92 protons, and it's an enormous amount of electrostatic repulsion. So that's why uranium here is very unstable to begin with, all right? So it's going to decay by beta minus. So what you have, this is the reaction here. You have this, you have the electron, you have the antineutrino. The antineutrino has no charge, right? And it's not a nucleon. So it'll be like 0, 0, if you like, okay? It's not in the picture here. Okay, so conservation of charge. So a conservation nucleon number. So you have 239 here. So you have 239. A plus 0. So, of course, like A is equal to 239. And the Z number, so you got like 92 here is equal to Z minus 1, right? And therefore, Z is equal to 92 plus 1 equal 93. So if you look up in your periodic table, what is element 93? Someone else? David already. You remember this from okay, some other people. Come on. It's easy. Give me. Give me. Who else? Come on. Some other people. Yeah, Catherine.
Neptunium.
Neptunium, that's correct. And it's going to be Neptunium what?
90. Wait. 239.
That's correct. Neptunium 239, right? So is it NP? I remember.
Yeah.
It's NP. All right. So NP 239 93. Very good. Very good. Nah, it's not a very nice P here. Okay, how much do we have? Okay, good. There's also another form of beta decay. It's called beta plus. In beta plus, it's the other way around. A proton will become a neutron. So that's the next one here. So a proton will become a neutron. Well, now you start with +1 and you end up with a no charge. So you cannot create or destroy like charge. So there must be something here. There must be like a creation of something that has a positive charge. All right. So what we have here, this is called an anti-electron. It's an electron, same property as an electron, but instead of having a negative charge, it has a positive charge. This is also called a positron. So an anti-electron is a particle of antimatter. Okay, so talk about this next year. So it's exactly the same as an electron, except that the charge is different. It's exactly opposite. All subatomic particles have an anti-partner. So you have a antiproton. An antiproton has the same property as a proton, except that it's negative instead of being like positive. Does anyone sort of might guess here what might this be? Just check like the previous one. Yeah, they?
Is it a neutrino?
Yeah, this one is a neutrino. This one here was an anti-neutrino. You can see here there's a little bar on the top. So bar means an anti. So it's a neutrino. That's correct. And it has no charge and it's not a nucleon. So A number is 0 and the charge is 0. Okay. All right, so if a proton becomes a neutron, you have one less proton, so it becomes Z minus 1. And to compensate for this, there must be a particle with a positive charge, which is a positron. So let's do this one here. Find the unknown elements in the beta plus decay of potassium 40. Well, once again, the A number doesn't change because you go from a nucleon to a nucleon, so nothing changed. All right, so that's going to be A40. And the Z number, so conservation of charge, you have like 19, right? Must be equal to Z plus 1. The neutrino has no charge. So that means that Z is equal to 19 minus 1. It's 18. And if you look this up, I think it's going to be argon. Am I correct? Yeah, argon 40. All right. Is that okay? Okay, so the third type, it's called gamma radiation. So you're all familiar with gamma radiation. That's what turns like Bruce Banner into Hulk. Gamma radiations are is a radiation that is very, very, very potent. Carries a lot of energy, lots of energy. So the reason why they use like gamma radiation to show that Bruce Banner becomes the Hulk is because gamma radiation can change the DNA structure, right? And that may be like one reason, that may be one mechanisms by which evolution works, right? So gamma radiation from some time to time change the DNA, change the gene, and this gene might might confer an advantage to the living things. So an advantage, reproductive advantage, so it's more likely to reproduce than other ones, and blah 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 blah. Anyway, okay. So here, like, you have to listen to me here. Well, let me sort of put it here. Don't write this down here. No, not this, not this, not this. There we go. So remember in chemistry, let's use a hydrogen atom here. Okay, so you got hydrogen atom. All right, so proton here, and then you have little electrons going on orbit, right? And this is called the ground state, right? Remember? You've all done like chemistry. Okay, when you excite, when you say we excite a nucleus, what it means here is means that you supply energy so that it jumps to a higher state, right? A higher orbits. Remember this, right? So when it's on the second orbits, we say it's an excited state. Now, what happens to the electrons on a higher orbits? What happens? Once the electron's in a higher orbit, what happens? Come on, you've learned this in chemistry. What happens? Yeah, Timothy.
Once it returns to its ground state, it releases a photon.
That's correct. So once the excited state comes to ground state, it releases energy in the form of mostly light. Okay, light energy. Okay, so in the nucleus, there are also ground states and excited states. There are also nuclear orbitals in the nucleus. Okay. So what happens is sometimes the nucleus will gobble up one of its own electrons. Electron that is like closest to the nucleus will gobble up, and then we'll combine this electron with a proton. So you have a negative charge and positive charge, and form a neutron. So this is the example here. So you have your nucleus here. It's going to gobble up one of its own electrons, and then it's going to form this here. So conservation of charge, A plus, conservation of nucleon number, A plus 0, A. So it's the same nucleon number. Z minus 1, of course, it's going to be a new element. But this one here is an excited nuclear state. Just like when the electron jumps to higher orbits and excited atoms, it doesn't stay there long, it comes back down. And as it comes back down to a lower energy level, it releases energy. Same thing here. When the excited nuclear state comes back to its ground state, it releases energy in the form of gamma radiation. And this gamma radiation is way more energetical, carries much more energy than light. Okay. So here, this is the ground state, the ground nuclear state. Now, gamma radiation is not a nucleon, so it's 0. It doesn't have any charge too. So basically, you go from A plus 0 is equal to A, and Z minus 1 is equal to Z minus 1. Okay? So let's do this here like very quickly here. So find the unknown element in the alpha decay of lead-211. So lead-211, so once again, it gobbles up its own electron, turns this into something that is excited. It comes back down and releases gamma radiation. So by conservation of nucleon number, 211 plus 0 is equal to A, right? Plus 0. So A, of course, is 211. And then by conservation of charge, you have 82 plus minus 1. So 82 minus 1 is equal to Z. So that gives you 81. And then you look up what 81 is. 81 is thallium. So thallium. So it's going to decay in thallium 211 or TL or TH. It's TL. All right, so TL 211 81. Are you good? Everyone is okay with this? Okay. Yeah, Madhav.
In this case, how come the Z number goes from 82 to 81?
82 to 81?
Yeah.
Because by conservation of, so you start with 82, it gobbles up an electron, so 82 protons and minus electron, 1 electron. So 82 minus 1 will give you 81, right? So what happens here is that one proton, okay, so you have 82 protons. So you have 81 proton plus another proton. This other proton here will combine with the electron to form a neutron. So that's why you have like one less proton than before. Is that okay? Yes?
Yep.
Yeah, okay. Okay, guys, so you've learned about logs, right? Well, I've talked about log plot. So you've learned about logs, right, in math? Everyone is okay with this? Yes or no? Yeah? Okay. All right. I don't know. You're not telling me much here. All right. So let's do the last part here. Okay. How do we measure the radioactivity? So radioactivity, once again, a radioactive nucleus is a nucleus that is not stable, that will sort of break down into smaller fragments that will decay into other fragments, other nuclei or other particles. Now the measure, so imagine here you have like a substance, a radioactive substance. Okay. So you have millions and millions of nuclei here. And let's see the substance is radioactive. So it means here that each of those nuclei has a likelihood of breaking down into other parts. In other words, here, if you have a uranium, a little pellet of uranium, some of the uranium nuclei will break down. So there'll be less uranium nuclei as time goes on. All right. Now, it so happens here that even though it's radioactive, it so happens that you cannot know when this particular nucleus will break down. It's a completely statistical process. You just cannot tell. Okay, so it's impossible to predict when an unstable nucleus will decay. So radioactive decay is a completely statistical process. However, there's a relationship that exists between the number of nuclei that decays. So N is the number of nuclei you have in a substance. Delta N is the change right? So as it decays, there's less and less. So delta N is negative here. There's a relationship that exists between the number of nuclei that decay and the time it takes. All right. So the number of nuclei that decays in the time delta t is actually proportional to the number of how many nuclei you have you're starting with. So what it means here, it means that the more radioactive substance you have, the greater number of nuclei will decay in a given amount of time. Okay. And so since it's proportional here, there's you put in front a constant of proportionality. The minus sign here tells you here it decays, so delta N like goes down, number of nuclei goes down. The constant of proportionality is like gamma here, and it's called the decay constant. So decay constant, each and every material have different decay constants. Now, so you should sort of, if you've learned about differential equations, do you have a question, Madav? Because your hand is still up. No? Yeah, okay. Raise hand. Do you have a question, Madav?
No, sorry.
Okay. All right. Now, whenever you have a relationship like this, where the change in numbers is proportional to how much you have initially, you can turn this into a differential equation, blah, 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 blah. And when you solve for this, this is what you get. Okay, so you should be familiar with this. All right, you don't have to write this down, but this, if I put it in this way, right? So this is like dn. So if I bring like the delta t on the other side, what I have is something like that, right? And so which function where you differentiate, you get the same function? Well, you know, it's the exponential. And here, this is the constant here. So that's going to be like your little constant there. So this is a solution to the above differential equation. So here it tells you NO is how many nuclei you have to begin with at a certain time. And N is how many nuclei you have left. All right, so you have left after a certain amount, delta T or T. Okay. Now, half-life is the amount of time for a radioactive substance to lose half of its original mass. Okay, half of its original mass. So let's do it. Okay, so let's do a simple problem here. Any question for this? By the way, that answers your question, Max. Okay, so well, no, just wait. Okay, so if we start with 20 grams of uranium-238, where its half-life is, okay. Sometimes, I don't know which symbol they use in your textbook. Sometimes the half-life is given as this here, T with a little half. Sometimes it's given as this. But in this case, we're going to put it as T subscript half. So just change this, guys. I apologize for that. So we're going to change this. So this is going to be T half. This is a little bit like technical. This is a little bit like a difference here between like the tau and T half here, half-life. All right. So the half-life of uranium is 4.45 times 10 to the 9 A. A stands for year. Okay, so that's a symbol for year. It's annum, Latin. Okay, so if the half-life is the amount of time for a radioactive substance to lose half of its original mass, then after this amount of year, after 4.45 times 10 to the 9 years, how much mass of uranium-238 would remain? So it's not a tricky question here. So how much would remain here, guys? Is it I don't have my... So Max?
10 grams.
Yeah, 10 grams, right? So there would remain only 20 gram over 2. Very good. All right. Okay, now guys, if I ask you after another half-life, how much material would there be left? Yeah, someone else, Day. It's always the same people though. Yeah.
5 grams?
5 grams. After another half-life, how much? Day again?
2.5 grams.
Yeah, and so on and so on. All right. So it's an exponential decay. That's what it's called, an exponential decay here. Okay. Now, activities, the amount of radioactivity is measured by a unit that's called activity. All right. And the unit of activity is called the becquerel. I don't know did I put it somewhere? No. Okay, it's called the becquerel. And the becquerel here, the activity is the number of nuclei that have decay per unit time. That's what it is. Okay, so here, this is the formula. This is the activity at some given time, A. This is the activity at some initial time. Yes, chat. It's at the top. It's at the top. Oh, yeah, yeah. So it's measured, unit activity is called the becquerel. Thank you. Thank you. So, yeah, so this is the equation here. If you want to put it in this form, you can put it in this form as well. Okay, so this is, so AO is the activity at a certain time at t equals 0. If you want to put it in this form, this is also correct, right? So t over t half, okay? So the whole exponent here is time over the half time, okay? And you also have in terms of mass, so instead of being in terms of how many nuclei left, you have in terms of how much mass is left. So how much mass is left is equal to the mass you had at time t0 times this, okay? And so on and so on, okay? Now, the relationship between the half-life and the decay constant, remember decay constant was this number right here, like right here, alpha here. The relationship between the two is this, okay? Is this. Okay, so let's do the last questions here. So find how much mass of lead-212 is left after 3 days if you started with 100 grams. And the half-life of lead-212 is 10.6 hours. 10.6 hours. So we're going to write down what we know. So what we know the initial mass of this at time t0, it's 100 grams. We know also the time, right? So t, I should have,
Sir?
yeah, yes.
Are we supposed to capitalize the M now for mass?
Well, sure, you can, in this case, you can put it big M if you like.
Okay.
The time, I should put delta t here, but the time is three days. All right. The half-life is 10.6 hours. Okay, and what you're looking for this. Okay, notice here that it's a ratio, t over the half-life. If it's a ratio, then it has to have the same unit of time. So either you change this into hours, you change this into days. Well, it's a lot easier to change like days into hours. So that's exactly what I'm going to do. So you got 24 hours per day, and I'll give you 72 hours, right? So it's very important that the half-life and the time be the same. All right. Okay, so once you have this, which formula are we going to use? You're going to use, of course, this formula right here. All right, so M equal to MO 0.5 T over half-life. Let me do a better job here. So T over this. And then you put the values. So let's put values, whoops, let's put some values here. So this is 100 grams, 0.5 Now raised to 72 hours divided by 10.6. Now you don't have to put the hour because the hour will cancel. Okay, let me put this a little bit, like I don't have space here. Okay, so 100 gram, 0.5. Will be 72 divided by 10.6. So you do PEDMAS here, you do the brackets, right? So figure out what 72 divided by 10.6 is. So let me see here, 72 divided by 10.6 gives you about like 6.79, right, roughly. Now you have to take 0.5 raised to the power 6.9. Now in your calculators, you might have like something that looks like this, or perhaps something like this, all right, in your calculator. And so either you enter like 0.5, and after you enter your exponent, or vice versa. I'm not so sure how it works here, but if I do in mine, 0.5, now let me see here if it works. Yeah, so if I do this here, what it gives me 100 gram times 0.00990. Okay, did everyone get this? It's very important that you know how to use like your calculator, guys. All right, everyone is okay with this? You got that here?
Yeah.
Okay, and then you multiply this together, so 2, so you end up with only 0.9 gram. So after 3 days of this radioactive substance, you end up only with 0.9 gram. Are you good? Any questions for this? Okay. Sometime you have to go the other way around too. I'm going to do this like very quickly here. So if I come back to this, sometime you might be asked like the following here. Find how much time we'll use the same how much time lead, how much time, okay, let me see here, find how much time, sorry guys, so find after how much time, this is so bad in English, find after what time, how much time, find after how much time led to, what was it again? Led 212. So find after how much time 12 is reduced to, let's see, 10% of its original mass. All right, apologize for the bad English here. But then again, it's only English. All right. And it's going to be the same half-life, which was, what was it? 10.6. So 10.6 hour. Yeah, hour. Okay, so notice here, you're not given the mass, you're not given the initial mass, you're not given the mass after some time, right? So, but you want it to be reduced to 10%. So what does it mean here? It means that the mass after this much time is only 10% of what it was before, right? So it's going to be this. So if you use the equation, it's going to be that. And now what we're going to do here is, of course, we can put like 0.1 m. And of course, m here goes away. And why don't you tell me I made a mistake here? You checked out, guys? 0.1 MO. There we go. And I put this. Now, does anyone know how to lower the t down, because it's an exponent? So what do we do, guys? You should have learned this. Yeah, Max, there we go.
Logarithm.
Yeah, we do exactly this. So you take the log on both sides. And then what happens when you do log? Of course, it comes back down. Very good. And then if I isolate for all this here, so I'll do this like a little bit fast here. So you bring the half-life right here. And it's going to be a log of 0.1 divided by log of 1/2. Then you put this in your wonderful calculator here. So 10.6 hours. So log of 0.1 is -1, is it? So log here, of course, divided by 0.5 log, which is this, and that gives you that, right? So times 10.6, and I'll give you 35.2 hours. So after 30.42 hours, the object here, this mass, this lead, will have lost 90%. It will be reduced to only 10% of its original mass. Okay. Okay, question. I apologize here. It's a little bit long. It's almost 15. Yeah, Madav?
I have a question about the constants used in one of the formulas.
The what?
The constants used in one of the formulas.
Yeah.
What do the lambda and E stand for? Is it E just as in like
Lambda. You don't know this, guys? It's the exponential. The E?
is it just the constant E like we use in
Yeah,
financial math?
it's E. E is equal to what? Like 2 point something? Like,
Okay.
don't remember. You know what it is?
Mm-hmm.
Yeah, that's a natural. Yeah, natural log. You remember? Like natural log. I don't know. Have you learned this in math? I'm not so sure.
I just wanted to check. And then
Yeah, that's what it is.
Lambda.
Lambda is the decay constant. So this is like. So what happens here is that the amount of nuclei that decays in a given time is okay. The amount, the rate at which radioactive nuclei decay is actually proportional to how many nuclei you have. So the more nuclei you have, the greater the rate at which those nuclei will break apart, will decay. Okay, and so you have a constant proportionality, linear proportion, direct proportional relationship. So you can turn this into an equation, and the constant proportionality here is called the decay constant. Is that okay? All right. So that's sorry, times n. Really tired today. Times n. Okay, and it's minus because it decays, right? So is that okay?
Yep. Thank you.
Yeah. Okay, guys. So you have like some questions to do, and that's it. Yeah, we're done with energy. So Monday, we'll start electricity. So there's a big package, about 11 pages. So please like download this for Monday. Okay. So questions? Apologize here. It's a little bit long today. Yeah, Max.
So no like element can completely decay to zero, right?
Well, I mean, like it's not infinite, right? So I mean, you have a material, you have a certain amount of nuclei in it, right? So eventually, like it will all disappear. But it takes a long time for some. So you asked me like how could those radioactive material be present? It's because some of them have a super long half-life. So some substances here have a half-life, or I don't know, like 10 to the 6 years, right? So before like this element like loses half of its mass, 1,000,000 years have to gone by. So that's why like this element here, like this substance, like stays for a long time because it decays very slowly.
But in that case, like, so how do you like get to having this radioactive like material in the first place, then? If it's like naturally unstable, like
it is formed. All right, so it is formed. Like I'm not going to go through the process by which elements are being created, but basically what happens here is that in the by process of what is called nuclear fusion in stars. All right, so you got like, let's say you have two hydrogen atoms that are fused together and then becomes like helium, and then it releases a lot of energy for a reason that we're gonna learn next year. And then like in the stars, like they can take the helium and two helium, like four, and fuse them together, and then it's gonna form like four. What is four? What is the element four? Four is beryllium. There we go. So it's going to form beryllium and so on. So this is how like elements are being created in the core of stars, and so some are more stable than others. Okay, so it depends on how many neutrons there are in it. So some substances are a bit more stable than others. Some are really unstable. So within a fraction of a second, they're going to sort of split into more stable components. And some are stable enough to last like millions of years.
All right, thank you.
Okay, I'm not going to get too much details here, but that's this. Okay, guys. So I'm going to stay by, and so do the problems, and I'll see you on Monday. Okay. So have a great weekend. Okay, it's going to be nice Saturday and Sunday. So enjoy it. Go outside. Stay safe though. Keep your distance. Go outside and get some fresh air. Okay. So bye-bye, guys.
Let's have a nice
Sure.
weekend.
Yeah, I'll stay here a little bit here if someone wants to ask.